So this is a video looking at circular motion for A-level physics. Within this tutorial video we're going to learn how to describe angles in radians rather than degrees. We're going to make sure that we understand the difference between linear velocity and angular velocity. We're going to apply the concepts of frequency and period to circular motion. We're going to be able to calculate angular velocity, constant speed, centripetal acceleration and centripetal force of an object in circular motion and look at the equations that we use to do that. And we're going to define and derive expressions for centripetal acceleration and centripetal force. As always, whenever we're doing these tutorial videos, remember, use the pause button, take a break, rewind, look at things again if they didn't quite make sense. Make sure that you make summary notes to accompany the video. You might want to watch it through once and then write the notes as you go through a second time, and make sure if you have any questions that you bring them to the next lesson. So we have briefly seen the concept of circular motion in GCSE, but it was all very qualitative, and we looked at the idea that if you've got an object or a body moving with a constant speed in a circular path, we did look at the idea that because even though the speed was constant, because the direction was changing, that meant that the body was accelerating. And if something is accelerating, there's going to need to be an unbalanced force causing that acceleration. And we looked at the idea that the force is always going to act towards the centre of the circle at right angles to the velocity. And you looked at a range of situations where we saw that different types of force could provide the centripetal force. And remember, the centripetal force is merely a force acting on the object towards the centre of the circle. It can be provided by lots of different types of force. So it could be provided by tension, gravity, friction, etc. So what we've got here is just a quick animation of the Ladybug Revolution on FET, which is really, really helpful for this, so do go and check it out. And what we want to start thinking about is applying Newton's laws to the situation of circular motion. So we mentioned before about this constant speed, but because we've got the direction change, that means the velocity is constantly changing. So the object travelling in the circle is accelerating. And we know from Newton's first law that an object will carry on in its state of motion until it is acted upon by an unbalanced force. And so we have to have the unbalanced force here to keep changing the velocity, to keep changing the direction so that it travels in a circle. And the force always acts to the centre of the circle, as does the acceleration. If you think about, if I pause this for a second, if we think about what you have to do here to get this velocity to change into this velocity, to change into this velocity, to change into that velocity, you need to keep accelerating it towards the centre of the circle. So the acceleration is towards the centre of the circle, and therefore the resultant force is going to act towards the centre of the circle as well. So far we've been describing circular motion, and that's what we were doing at GCSE in words. But obviously now that we're moving into circular motion in the A-level course, we want to take that one step further, and we want to be able to quantify circular motion in different situations and use it to solve a variety of problems. The first stage to being able to quantify circular motion properly is to move from using degrees to measure angles to using radians. So a radian is a very mathematically intuitive way to measure an angle. So it would effectively be like an SI unit for an angle, though it's not one of the SI units. The definition is the angle subtended by a circular arc with a length equal to the radius of the circle. So if we see here, if this is the radius of the circle, we're saying if we think of an arc that's the same length as the radius, whatever that angle is in there, that is 1 radian. So if you make the circle bigger, that arc will get bigger, but the radius gets bigger as well. And so actually you find that a radian is always equivalent to about 57.3 degrees. If you want to convert between the two, the angle in radians is the arc length divided by the radius, so that's how we calculate it in radians. And we know that if we looked at a whole circle, so if we imagine the arc length was the whole circle, that's the circumference, and that's 2 pi r, okay? So if we had an arc length of 2 pi r, and we had the number of radians in that whole circle, that's 2 pi radians, so if we do 2 pi r divided by the radius r, then we get 2 pi radians in a whole circle, So the arc length for the whole circle would be 2 pi r. We divide it by the radius, just according to this equation here, and that gives us 2 pi radians in a whole circle. So 360 degrees is equal to 2 pi radians, and 180 degrees is equal to pi radians. So before we go any further, I want you to have a look at this video and just have a think about the motion of these different Lego blocks here, okay? And I want you to think essentially about how fast they're moving and what their velocity is. So we're trying to keep the turning of the circle as constant as possible within the realms of what is possible in a kitchen. And what hopefully you can see when you've had a look is that they were all doing one complete revolution in the same amount of time, but this one was travelling a much further distance in that time than this one was. And we need to now find a way to accurately represent that in the terminology and the formula that we're using. So what we're going to do is we're going to introduce the concept of angular velocity, okay? And this combined with the idea of linear velocity will allow us to describe the different motion that we see in a circle. So angular velocity, we've got our circle here, we've got our object, and it is going to pass through a certain angle here in a certain amount of time. And the quicker it's moving in a circle, the less time it will take to pass through that angle. So we're going to denote the angular velocity with omega. It's measured in radians per second, and it is the rate of change of the angle. Okay, the equation for it looks like this. So we've got angular velocity is equal to the angle divided by the time taken to pass through that angle. Now, if we now apply our ideas about period and frequency from, way back when we started learning physics, we know that period, T, capital T, is the time for one complete oscillation. So that would be the time to get from here all the way around the circle and back again. So, and from what we've just seen as well, we were saying that the circumference of the circle, in terms of, when we were describing it in terms of radians, we know that this angle here is going to be 2 pi radians because it's the whole circle. So if we put that in here, we've got the angular velocity is equal to 2 pi over t, the period. And we know from previous work that frequency is the number of oscillations per second, and it's the reciprocal of the period t. So if we substitute this into here, we can get the angular velocity is equal to 2 pi, the frequency, the number of revolutions per second. So on the video clip with the Lego bricks, what we saw is that all 3 Lego bricks had the same angular velocity. They were all taking the same amount of time to turn through a certain angle. But we could see that the Lego brick on the outside of the circle looked as though, visually, it was travelling faster than the inside Lego brick. And that's because they had different speeds, they had different linear velocities. So let's have a little look at how we can take account of that now. We know, from year 7 that speed equals distance over time. In the case of a circle, we're going around this diagram, the distance travelled for one revolution is equal to the circumference of the circle, which is equal to 2 pi r. And we know that the time taken to travel that distance of the circumference is the time taken for one complete revolution, so that is the period. So if we put these two expressions into speed equals distance over time, we are left with v equals 2 pi r divided by t. And in this case, v is our linear velocity. This is measured in meters per second, unlike angular velocity, which was radians per second. Now we know from our previous slide on angular velocity that the angular velocity is equal to 2 pi over t. If we substitute this in to this expression for linear velocity, we get the linear velocity is equal to the radius multiplied by the angular velocity. Now what this means is that if we had 3 objects, so you can imagine these were the 3 Lego bricks at different radiuses or radii from the centre of the circle, the linear velocity is directly proportional to the radius. So if you double the radius, you're going to double the linear velocity because they've all got the same omega, the same angular velocity. Okay, so our next job that we wanted to do within this tutorial is to derive and find expressions for the centripetal acceleration and the centripetal force. So it's worth just reminding ourselves of what those are and defining them. So we've got our circular motion here. Here's our object. It has velocity, linear velocity v in this direction. The acceleration always acts towards the centre of the circle, as does the force. It's travelling around in this circle here. And just to state it really, really clearly so we're all clear, an object moving in a circle can move at a constant speed but have a constantly changing velocity. This is because the direction it travels in is constantly changing. Therefore, it's constantly accelerating. Therefore, a net force must be acting. So our centripetal acceleration, we're saying the acceleration of any object travelling in a circular path at constant speed, which always acts towards the centre of the circle. And our centripetal force, a force that keeps a body moving with a constant speed in a circular path. So we find that the acceleration of the object, the centripetal acceleration, is dependent on the linear speed, so the linear velocity, v, and the radius. If we increase the linear speed, we increase the acceleration. And if we make the radius smaller, we increase the acceleration. And we get this expression here. So the centripetal acceleration is equal to v squared divided by r, the radius. So it's equal to the linear speed squared divided by radius. If we substitute in our previous expression for v, so v equals r omega, and we put this in here, we get the centripetal acceleration is equal to r omega squared divided by r, which simplifies down to the centripetal acceleration is equal to r omega squared, so the radius multiplied by the angular velocity squared. Now, if we use F equals ma and the expressions that we've just seen for centripetal acceleration, we can get our expressions for centripetal force. So, based on F equals ma, we're going to substitute in for a. So first of all, let's substitute in the centripetal acceleration is equal to v squared over r. So when we put that in to F equals ma, we get that the centripetal force is equal to the mass times the linear velocity squared divided by r. Okay, and if we have a think about what this is telling us within circular motion, if the mass is staying constant and the radius is staying constant, then F is proportional to v squared. We can also substitute in this expression for centripetal acceleration. The acceleration is equal to omega squared r, and when we put this expression in here, we get this expression for the centripetal force. The centripetal force is equal to the mass times the angular velocity squared multiplied by the radius. Now, if we have a think about what that means in terms of how the centripetal force changes with radius, and we have a look at the next video, then we can see that a couple of things start to make quite a lot of sense. So here's our expression for centripetal force. Centripetal force is equal to the mass of the object multiplied by the angular velocity squared multiplied by the radius. So if we have a look at this situation again, we've got our 3 Lego blocks. They've each got an equal mass. They're the same Lego block essentially. And they're going to have the same angular velocity, but what's changing about them is the radius. Let's have a look at what happens. As we start spinning them faster beyond a certain point, the Lego blocks will fly off. So as the radius increases, the centripetal force needed for it to travel in a circle will increase as well. Now in this situation, the centripetal force was being provided by friction between the Lego blocks and the marble spinning top. And when that friction is no longer big enough and the centripetal force is no longer being provided, the object will stop travelling in a circle because the centripetal force needed isn't being provided, and so they fly off. Now this links us into one of the most common examples of questions and problems that you'll see on centripetal acceleration within the A-level course. And that's looking at things travelling around corners at speed, as we just saw, but the use of banked surfaces. So a banked surface is where a corner has been raised up from horizontal up towards the vertical to help things corner at speed. So a really good example of this is the train track at Clapham Junction. Lots of trains don't stop at Clapham Junction, they go straight through, but it's on a corner, it's on a bend. And so if you ever get off at Clapham Junction, you can look at the train track and you'll see that it has been put on a bank so that the trains can travel at greater speeds through Clapham Junction station. And what's happening with a bank track is that because the frictional force isn't big enough to provide the centripetal force needed for the mass and the angular velocity of the object and the radius of the curve, by banking the surface, you get a horizontal component of the normal reaction force on the surface. So look at this cyclist here. Imagine a velodrome in the Olympics. All of those curves are banked because you've got the weight of the cyclist acting vertically down and you've got the normal reaction force acting perpendicular to the surface. By banking the surface, the normal reaction force now has a horizontal component which acts towards the centre of the circle, which provides the centripetal force required to go around the bend at speed, rather than just relying on friction alone. So this is a situation we need to do a lot more practice on, but that's the essentially the basics of it. Another common situation that comes up in problems involving circular motion at A-level is that of vertical circles. So far we've been looking at everything horizontally, but if we start looking at vertical circles within gravity, we can see that the situation is going to change from the top of the circle to the bottom of the circle. So let's just have a look at this now quickly, and then we can do more practice on problems involving this situation in lessons. So we've got this object here, it's travelling in a circle. You can see we've got velocity vt and vb here, just stands for top and bottom, but that velocity is going to be the same, so vt and vb are equal. Here's the centre of the circle. We also know that because this is a vertical circle, that weight is acting on the object. So you can see I've marked on the weight here mg, and it's acting down here mg as well. And we know that because this object is moving it in a circle at a constant speed, there is a centripetal acceleration. And in this example, that centripetal acceleration is provided by tension in a string. So this might be a ball that I'm waving around on a piece of string, or a conker in a vertical circle. So I've got tension of the string acting towards the centre of the circle here, and tension on the string acting towards the centre of the circle here, and I've labelled it tension top and tension bottom. So let's have a think about what's going on. At the top of the circle, we know that the centripetal force is equal to mv squared over r, and in this case it's Vt. Okay, so F equals m Vt squared over r, and we know that that centripetal force is the force acting towards the circle. So in this case, that is T tension from the top plus the weight, which is acting down towards the centre of the circle as well. So here you can see we've said m Vt squared r is equal to tension from the top plus mg, the weight. We simplify that all around and we get this. The tension in the string here is equal to the mass of the object times the velocity squared over r minus the weight of the object. But if we look at the bottom of the circle and the expressions for the bottom of the circle, we see that, again, centripetal force is equal to the mass times the linear velocity squared over r. And here you can see that the centripetal force is equal to Tb minus mg. Okay, so when we rearrange that, we get the tension in the string at the bottom is equal to the centripetal force plus the weight. So at the top of the circle, the tension in the string is equal to the centripetal force minus the weight. And at the bottom of the circle, the tension in the string is equal to the centripetal force plus the weight. So the tension in the string is going to vary here at different points in the circles. This can also apply to roller coasters. So the contact force between the roller coaster and a track, if you had a sort of a loop-the-loop roller coaster like this, rather than tension, it's going to be contact force. So the normal contact force will be different at the top and the bottom, and then the two sides of the circle. So again, we need to do lots more practice with these situations, but this is what we have to be thinking about when we see those challenges. So let's just recap on the things that we were aiming to discuss in this tutorial. First of all, we wanted to be able to describe angles in radians. We wanted to understand the difference between linear velocity and angular velocity. We wanted to be able to apply the concepts of frequency and period to circular motion. We needed to be able to calculate the angular velocity, the constant speed or the linear velocity of the object, the centripetal acceleration acting, and the centripetal force. And we wanted to be able to find and derive expressions for the centripetal acceleration and the centripetal force. And we've done those things. Now, obviously, this is just an introduction. We need to go and do practice questions and make sure that we can apply this. But please can you make sure that you have got summary notes on the concepts that we've been discussing in this video, that you write down any questions that you have and you bring them to the next lesson so we can discuss them. Brilliant, well done. See you in the next lesson.